Welcome to the ultimate session of the 3 days continuous program for the periodic table day, as we call National Periodic Table Day, to commemorate the remarkable contribution made by so many scientists, beginning from Newlands, maybe Doberiner, Newlands, and Dmitry Mendeleev, Lothar Moseley, and the latest scientists like Seaborg and many others. Today, we'll be taking up the discussion on radioactive elements. So, let me share my screen. Radioactive elements, natural and synthetic. Now, before that, I would like those who are watching to see to draw the periodic table once again in a landscape mode, in a blank sheet. You pick up a blank sheet, don't put any lines. We shall see how much proficient we are, that we can prepare the periodic table even without drawing 7 rows or periods and 18 columns. So welcome, Anisha. So today's discussion will be the concluding part of the periodic table, how the radioactive elements, the synthetic radioactive elements, as well as those elements which were there, now extinct, they have been also prepared synthetically. We'll be knowing that. But before that, Anisha and others, Sif and others who are watching, let us try to remember that song. We'll not play that song, but let us try to draw the periodic table. Don't look at the periodic table in front of you. I will remind you if you fail. Hydrogen, helium. Write down. We'll not draw any periods, any lines, vertical, horizontal, nothing. We'll just generate the periodic table, align the elements properly so that there will be no problem at all. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, boron, carbon, nitrogen, oxygen, fluorine, neon, number 10. Done? Done? Anissa, done? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Nitrogen, oxygen, fluorine. neon, number 10. 1, 2, 3, 4, 5, 6. Then third period. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, number 18. Sorry. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, 18. Fourth period. Fourth period is beginning from which element? Shiv?
Sir, potassium.
Yes. Potassium, calcium. Then starts the transition series. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Scandium, titanium, vanadium, chromium. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, 36. लिख दे लो डन डन पोटासियम कैल्शियम स्कैंडियम टाइटानियम वैनेडियम क्रोमियम मैंगनीज आयरन कोबाल्ट निकल कॉपर जिंक गैलियम जर्मानियम आर्सेनिक सेलेनियम ब्रोमीन क्रिप्टन 36. Then we start fifth period. Rubidium, strontium, yttrium, zirconium, niobium, molybdenum, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon, 54. Rubidium, strontium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon, 54. Then we go for the sixth period. Begins with cesium, barium. Then immediately go for, you can write down lanthanum here, square it and round off. But we write down all the 15 lanthanides below the table. The first series of block elements, the lanthanides, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, Tm, ytterbium, lutetium. Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Let us just give it 71. This is 57, 71. This is 57. Then 72. Again, we have to take the name of lanthanum because our Melody is for 10 elements. If you lose, the melody will not be repeated. So one of the viewers yesterday asked me why you have repeated lanthanum and actinium 2 times. I said because to have the same melody. Lanthanum, lanthanum, hafnium, tantalum, tungsten, lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, then immediately thallium, lead, bismuth, polonium, astatine, radon, 86. Over. Cesium, barium, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, orbium, thulium, ytterbium, lutetium. Again, lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, thallium, lead, bismuth, polonium, astatine, radon, 86. Over, Anisa? Then francium, radium, francium, radium. Now actinium should be here. It is 89. This is 87, 88, 89. But we shall be writing lanthanides, actinides. This is the lanthanides, and this is actinides. We'll be writing beginning from actinium. Actinium, thorium, protactinium, Pa, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, formium, mendelevium, nobelium, Lawrencium, actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, formium, mendelevium, nobelium, Lawrencium. Then again we come back here. The same melody. Lanthanum, hafnium is that type. Actinium, rutherfordium, this will be 103 and this will be 104. Actinium, rutherfordium, dubnium, seaborgium, borium, hassium, meitnerium, dumstatium, roentgenium, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, organation, 118. So if you go through the melody song, I think 2 minutes. Actinium, rutherfordium, dubnium, seaborgium, borium, hassium, meitnerium, dumstatium, roentgenium, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, organation, 118. Over. See? And those who are watching
Yes, sir.
from the YouTube, uh, are you over? Please write to me in the chat box. Are you done? So, in the beginning, I wanted to review the periodic table generation, writing the 118 elements in melody without drawing any horizontal lines, vertical columns, nothing is required. We know, who can tell me, where are the radioactive elements? Yes, I have not muted you. You can open because today's program will be centering around the radioactive elements and the synthetic radioactive elements and natural radioactive elements and how they are synthesized. Something about radioactivity. Yes, Siv?
Sir, after bismuth.
After bismuth, everything. Okay, let me put a star mark. Polonium is radioactive. Astatine is radioactive. Radon is radioactive. Then francium is radioactive. Radium is radioactive. Actinium is radioactive. Actinium is here, radioactive. I'm repeating, so it is better to cancel now. Actinium is radioactive 89. Thorium is radioactive. Protactinium, uranium, neptunium, plutonium, americium. Again, I have done the same mistake I did in the first class. Curium is not Cu. Curium is Cm. Cu is copper. It is already here. You must have brought to my notice. I'm so sorry. So this is curium is radioactive. Berkelium is radioactive. Now let's start to put a different color. Tell me up to what elements the radioactivity is natural. That means nature has produced such elements. Nature has produced such elements. Doesn't matter that because of its low lifetime, small lifetime, few of them have been almost extinct and it is available in trace quantity. But they were there, they are also now present. Since they are present in trace quantity, we are not finding them. Instead, we are synthesizing them. So, up to what element? Yes? Siv?
Sir, bismuth, from bismuth up to neptunium.
No. Anisa? A little mistake. Namaskar, Anil sir. Good morning. You are,
Sir, up to plutonium.
yeah, up to plutonium, it is naturally radioactive. Polonium, astatine, radon, francium, radium, then actinium, thorium, protactinium, uranium, neptunium, plutonium, up to that, naturally radioactive elements. And then I will change a sign from americium, totally synthetic. So they are radioactive, but they are synthetic. So this is americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium, and then 104 is here. Rutherfordium, dubnium, seaborgium. These are completely synthetic, man-made. In the God's laboratory, earth crust or atmosphere, there was nothing called americium, curium, and all that. We have the human beings, the scientists have prepared them by some method that we are going to discuss today. That will be the interesting part. And then copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, oganesson. Now my question is, we have missed out another two radioactive elements before bismuth. Who can tell me? we have missed out two radioactive elements. Yes?
Sir, what are the technetium?
No. Anissa has raised her hand. Please, see, let us allow Anissa to.
Okay.
Anissa?
Xenon.
Huh?
Xenon.
Xenon. Are you kidding me? Xenon is not a radioactive gas or radioactive element. Radon, yes. Radon is because it is coming after bismuth. All elements after bismuth, they are radioactive, and up to plutonium, naturally radioactive. But since these are almost extinct, so we sometimes call up to uranium 92, uranium. This is 92. So these are called transuranic elements. From neptunium onwards, these are called transuranic elements. These, but practically the transuranic elements are from americium, because plutonium and neptunium, they are available in nature, but they are synthesized. Which two elements? Who can tell me? Those who are watching from the YouTube, can you write down in the chat box before I ask Steve, who is with me in Zoom, to tell the answer? There are two elements which are radioactive. None of their isotopes are stable. All isotopes are radioactive. That's the beauty. Before, now see to the nature's magical creation. All elements are stable excepting two elements before 83. You can write down in the chat box. No, no, no. Now, Vanessa, see and tell Sarthak that shortly after your examination is over, we are making a trip to your school. I will contact your Pradhan Acharya to have some program in your school so that the prizes will be distributed to you three who have attended and who have answered, interacted very well, the prizes. Just you finish your annual examination and be promoted to class 10. Yes, Siv.
Sir, technetium and promethium.
Yeah, technetium and promethium. Technetium is 43. Yes, this is 36. This is 37, 38, 39, 40, 41, 42, 43. Just put a round mark here. This is radioactive. Now it is almost extinct, scarce. So nobody bothers to get technetium from the nature. It is being prepared. I'll tell you how. Synthetically. And the other one is promethium. This is 57. You can write down the atomic numbers: 57, 58, 59, 60, 61. So this is another radioactive element. My another question. Those who are watching, and let me tell you that if you have watched little late, you go to the beginning, and we have generated the periodic table in maybe 5 minutes, but actually it should take 2 minutes, just like Maggie. Maggie, 2 minutes, because it is ready-made. You put it in the boiled water, and within no time it will be ready for eating. It will be very hot. You have to leave some time to cool, and then you eat. Very tasty. So if you remember the music, the song, it's not a difficult song, and then you can generate the periodic table in 2 minutes. And there are many instructors, teachers all over the world, they have, uh, devised some technique to remember the elements, but not all elements. Maybe 20, maybe 30, but not all elements. Here we have taken, in this case, all elements, and in US, the ASAP science, they have also uh, created a song for all elements. But that song, that for us, you will see that is very good to listen and watch. But for us, Indians and other non-native uh, English-speaking countries, it will be difficult for us to follow. So, but it's very good. One of the best productions. They have followed the very popular music, can can. It's called can can music. They have followed in toto. Yes, tell me any other elements in the periodic table before bismuth which contain, besides stable isotopes in abundant quantity, but a trace of a radioactive isotope. You understand my question? Tell me some elements before bismuth which are basically stable. 99% they are stable, but maybe a very little percent, they carry radioactive isotopes. At least you give two examples. There are many others, but at least you give two examples. Yes, anyone who are watching from the YouTube can write down in the chat box. See,
Sir, one is tritium,
uh-huh,
the H3, and
uh-huh.
another is
Is somebody prompting you? No?
no, sir.
Okay, good. Anissa? You knew it, you know it. It's not occurring to you. It's not occurring to you. Yeah? Anyone? In the chat box, you can write down those who are watching in the YouTube. They are hydrogen, one of the isotopes of hydrogen that is called tritium. Some people pronounce as tritium. Some people write as T13. Same. T13. 3 is the mass number and 1 is the atomic number. This is tritium, that is radioactive, that emits beta particles. And the other one, you are forgetting carbon 14. See, carbon 14, carbon has 3 isotopes. Carbon 6, carbon 12, carbon 13, they are stable. But carbon 14 has a bad atomy. It emits beta particles. And its half-life period is not small. It is 5,770 years. So every 5,770 years, it will be halved. So it will take a long time to completely die. And the other one, who can tell me the other one, which you are taking? Which you are taking every day in different minerals, in different fruits, vegetables. Who can tell me? Yes, Siv? Yes, Shiv? Anisa? Anisa? Anisa?
Oxygen.
Huh? What?
Oxygen.
No. Oxygen, all the three isotopes. Oxygen, all the three isotopes, 16, 17, 18, they are stable. They are not radioactive. I told you yesterday, or maybe day before yesterday also, you have attended, you are so good. You have attended all these lectures. Yes, that I give a clue that is present abundantly in bananas. Abundantly in bananas, I told you, because of that, our body is a source of radioactivity. We are not radioactive. We don't have any atom which are itself radioactive. But we consume the materials. Oh, yes. We have the body, the all organic compounds constitute our body is made up of carbon. Yes, we are radioactive. We are radioactive. We are radioactive. We are emitting beta radiation, not alpha, beta radiations. But we are not harming, we are not polluting the atmosphere, or we are not getting any pain or any adverse effect of radioactivity. Yes, what is that? Sif?
Sir, potassium 40.
Yes. I think you are taking the help. Anyway, doesn't matter. Potassium 40.
Sir, banana koila mone koila.
Ah, very good. The benefit of doubt will go to definitely you that you are genuine. Potassium has 3 isotopes, but 39 is the most abundant isotope, 99.99. But some 0.01% is potassium 40, and 41 is also there, that is stable. That potassium 40, and these are the 3 common elements which are, though its isotopic sisters are stable, but they are present in small trace quantities to make them radioactive. So our body is made up of carbon, hydrogen, and a lot of potassium we have, because all our cells, they need potassium inside and outside, sodium ion inside and outside. Otherwise the nerve will not function. If there is any imbalance between the sodium ion and potassium ion ratio inside and outside the cells, then we are gone. Okay, after having discussed, my next question is, tell me which elements can be both synthetic and natural. I have already told you, you have to tell me which are natural, but due to its scarcity, we are preparing it. Yes?
Sir, radium,
Hmm?
radium, technetium,
Radium, no. Radium, we are not interested.
technetium,
Technetium, yes. Technetium, yes. Then technetium is one of the most important radioactive, synthetic radioactive isotope now, technetium 99, which is used in cancer treatment, in SPECT. And then, yes, and then all before, all before americium. All before americium, I told you, just to put a line here, up to plutonium, they are natural. After plutonium, they are all synthetic. So those which are before americium, but some of them, they are available in abundant quantities, for which the earth is so very happy that we have a lot of such elements and their corresponding minerals. which will give us energy for thousands and thousands and thousands of years. Besides them, all others which are scarce, we are preparing. Then next one is the same. The promethium that you told, Steve, promethium is another radioactive element before bismuth that also is being synthesized. So these two are natural, just as a matter of convention, we have to say they are natural. They are prepared by God, I mean, the nature. But now, because they are available in trace quantity, we are synthesizing it because they are necessary. So technetium, promethium, and then
Sir, technetium, promethium, actinium,
yes, why
protactinium,
not polonium? Why not polonium? Yes, polonium. Polonium is radioactive. We are now synthesizing. Then
actinium,
astatine.
astatine,
Then
radon.
radon, we are not because it is being continuously produced because of the decay that we'll be seeing of uranium and thorium ores. We are not venturing to synthesize radon. Radon is available and it is increasing in the atmosphere. One of the pollutants in the atmosphere, particularly in the West, is radon gas. It is coming. It is being escaping from the earth crust to the atmosphere because it's a gas. So we are not synthesizing. Then
Neptunium, plutonium.
no. Francium, you're just jumping after radon, then francium, right? We are also synthesizing francium. Then actinium,
Actinium.
also synthesizing. But we are not synthesizing thorium because thorium ores are available in abundant quantity. And thorium is the next source of energy after uranium. Thorium and uranium, they are present in ores in abundant quantity throughout the world. So we will not go to synthesize thorium and uranium. So thorium and uranium is this not synthesized, but we are synthesizing protactinium and of course neptunium and plutonium. Of course. So how many elements are both natural and synthetic? Polonium, astatine, radon could be, but we are not synthesizing. Then actinium, yes. Oh, we forgot radium. Oh, I'm so sorry. Francium, radium. We didn't. We forgot to write radium. Radium, we are not synthesizing. Write down radium. Radium, we are not synthesizing because it is available in the uranium and thorium ores. We are not synthesizing, but it could be synthesized. Yes, it could be synthesized. Some of the laboratories, they are synthesizing different isotopes, synthetic isotopes of radium and francium. Oh, I should not give a square box. I should underline. No. I should tick. So francium, radium is tick and cross, but not much radium is being synthesized. And actinium, protactinium, neptunium, plutonium. My next question is up to which element the synthesis has been done in the bulk state. I mean, some measurable quantity has been prepared so that they can be used as target material for firing, hitting projectiles onto it. Yes? Any answer from the viewers from YouTube? Siv?
Sir, after plutonium.
No. You have forgotten that. That is why I'm revising today. No. Anissa, will you try? up to Californium. You just put another line like this up to Californium. Up to Californium, these are synthetic. Purely synthetic is from americium, curium, purely. Nature has never prepared this. We are doing. But interestingly, their half-life periods are quite high. They can stay for a longer time, and we can prepare, say, 5 gram, 2 gram, some milligram. So they will stay and stand and will be heat up and by other projectile at a lighter nuclides at a high speed to bring about transformation. So up to Californium, the elements are produced in state of bulk state. Now, after having revised, we will go to, a term called norm. Norm is naturally occurring radioactive materials, which you already know. Technetium 99, promethium 147, tritium, carbon 14, potassium 40, lead 210. Now, bismuth 209 we are not taking as radioactive. But recent study has revealed that bismuth 209 could be is radioactive, but its half-life period is so large, even 10 to the power 6 times greater than the age of the earth universe. I'm sorry, age of the universe. I told age of the earth. Earth was born much later than the birth of the universe. The birth of the universe is shorter than the half-life of bismuth 209. So we are taking this as stable. Polonium 210, astatine 218, radon 222. This is a dangerous noble gas. Nobody, takes the help of radon 222 for any application. Only we want that we should be freed of radon. Francium 223, radium 226. I have taken the relatively most stable isotope. When I say stable, I don't mean they are really stable. Least unstable. Let's say least unstable, having the greatest half-life period I have taken. But each of them has multiple radioactive isotopes. This lighter elements like potassium, carbon, hydrogen, they have only one radioactive isotope that I have mentioned. But others, polonium, astatine, francium, radon, radium, actinium, thorium, protactinium, uranium, neptunium, plutonium, they have multiple isotopes, out of which I have selected the one which is least unstable. Now, these, as well as all synthetic radioactive elements after plutonium, all are synthetic elements. Decay is disintegration. They are transformed to another completely different element with a different number of protons. That is called decay spontaneously. Oh, Mr. Jeffrey Herrera, you are from which place, Mr. Jeffrey? What advice do you tell students studying for MCAT? Oh, I'm so sorry. This is not the time. Please excuse me. I beg your pardon. That's not the forum where I can advise anything to the students who are appearing from MCAT. But by the way, Mr. Jeffrey, you are from which place? You're watching. Miami. Oh my God, Miami is a wonder place. I have stayed. I used to stay in US every year for 4 to 5 months with my children, but in the West Coast. In California, in San Diego. San Diego is a very, very good place weather-wise. It's a temperate climate. I enjoy the weather of particularly San Diego, Los Angeles, and that, of course, Los Angeles is being earning a very bad name because of the forest fire, which is taking a toll, heavy toll of not only lives but also properties. Well, thank you. Miami, I have never visited. I will definitely go to Florida and Miami. The Miami beach we have seen in movies, but not gone. I've gone to the East Coast several times, to New York, to DC, to Boston, to Chicago, and Cincinnati, and many other places in the Eastern or Near Eastern. But down south, Florida, I have a mind to go. Maybe in 2025, this year. That if we visit to our children, then I will definitely go to Miami. Maybe we can meet. So let me come back to radioactivity. These spontaneously decay guys who are watching, these naturally radioactive or synthetically radioactive elements, they spontaneously decay only 4 rays. Out of them, actually 3 are particles having mass alpha, beta, and positron. And the other particle is not a massive particle. I mean, not massive, massful particle. It is massless particle. The rest mass is 0, because this electromagnetic radiation, and the particle, it is called a photon. So that is a gamma photon. So that is not a particle. So alpha, beta, positron. And analogous to positron emission, we have another decay process, what we call K-capture or electron capture. I'll tell you everything today. Now, what are really alpha particles? We already know that this nuclear reaction, they occur from the nucleus, from the atomy, not from the periphery. Electrons which are in different cells, they are nothing to do with any nuclear reaction or nuclear transformation. Only the nucleus takes part. Now, alpha particle is nothing but a combination of 2 protons and 2 neutrons. That we call, it is helium, dipositive helium nuclei. So we write in the equation He2 4. Of course, this is an ion. Don't confuse. We don't put any charge in writing the nuclear reaction. We don't write any charge. Actually, alpha particles are charged particles with 2 positive. But when it comes out to the atmosphere, it grabs 2 electrons, because this atmosphere is a vast reservoir of electrons. So it turns into a neutral helium gas, but before its birth, let's just the particular radioactive element is giving birth, alpha, beta. Alpha is coming out from its nucleus in tremendous speed, and when it comes to the atmosphere, it picks up 2 electrons to neutralize it and becomes a helium gas. Now, beta particles, they are produced inside the nucleus. I told you, by the conversion of, right down here. No, don't write anything. If you want to write, it's okay, but I'll go with a speed so that we will be covering this within another half an hour. Within another half an hour or maybe 35 minutes, we'll be covering what we have planned to cover. Now, beta particle is analogous to electron. It is nothing but electron. But how? It is produced inside the nucleus. Nucleus has positive charge. They have positive charge, protons, and neutral particles, neutrons. So I've told you one neutron is transformed into a proton and a beta particle. Beta particle is, that is electron, and +1 -1 is 0, and 1 plus 0. Beta particle has a mass, electron has a mass, but we write it 0. But don't be swayed away with the literary, this 0. It is having a mass, but in the equation we write 0. It is almost negligible mass. But when we write 0 over gamma, it is really 0. The rest mass is 0. I'm not talking about the relativistic mass, but the rest mass is 0. But here 0, it is presumed to be almost negligible mass. So because of this conversion, proton remains inside the nucleus. So the new element that is produced will have one atomic number more. I forgot to tell you, when alpha particle is emitted from a radioactive nuclide, the isotopes are called nuclide. When an alpha particle is emitted out, the new element, new elements are very typically called daughter elements. I don't know why the scientists have coined the term daughter. Sometimes when the new element has one atomic number more, when there is a beta emission, how an element having more number of protons can be called the daughter of an element which has a less number of protons. Anyway, we will be also putting the word daughter element. Any element produced, any isotope produced from the mother isotope. The first isotope is called mother. Mother term is not used, but the daughter term is used. So when an alpha particle is emitted, the new daughter will be occupying 2 places to the left because it has lost 2 protons. 2 protons means the new daughter will be having a place 2 places to the left. And when a beta is emitted, because a proton is created inside the nucleus, proton is created inside the nucleus. So the daughter occupies 1 place to the right. And now another particle, positron, that is the antiparticle of electron. It looks like electron, is very thin, almost negligible mass, but it had a positive charge like proton. Therefore, its name is positron. But in the US, I've seen, because I've interacted with many teachers and scientists, they call it anti-electron. In British, we say, in India, we say anti, but they say anti. So they never, ever say positron. They say anti-electron. So that we call positron, which is having mass like electron, but charge like proton. So this is positron, which is the antiparticle or anti-particle of the electron. So when positron is emitted, how a positron is created? The nucleus doesn't have a positron. So the other way around, a proton is transformed into a neutron and a positron. This positron goes away with a tremendous speed, and since it loses one proton, the mass number doesn't change because a neutron is created, but the atomic number is reduced by 1. So this new element occupies 1 place to the left. Alpha, 2 places to the left. Beta, 1 place to the right. Positron, 1 place to the left. And gamma is not a particle, it is an electromagnetic radiation. There are so many ways by which a gamma is emitted. When an alpha particle is emitted, or sometimes beta particle is emitted, the nucleus goes to a higher level. higher energy level, what we call the excited state. It doesn't go from its own position. I mean, it acquires more energy. We are not going to the details how to calculate the energy, what is the decay energy. We are not going to study that. Just I am telling you in a qualitative manner that the nucleus, after ejecting alpha or beta or positron, it acquires little more energy. Still, it has not reached the ground state. So when it returns to the ground state, that extra energy that the nucleus is possessing, when it comes back to its normal ground state, it emits a energy photon that comes in the range of gamma. Because you know the electromagnetic spectrum, starting from the cosmic, then gamma, then UV, you know the spectrum. So the gamma has a very high energy, low wavelength radiation, and photon is emitted. So I will be telling you interesting facts. A 70 kg person, a 70 kg, maybe those who are students, and particularly in India, they often are not 70 kg. They are much less. I mean, if you are a girl, then you might be around 40, 45. Or if you are a boy, then hardly 50, 55. This is the average. I'm not talking about the obese guys, which in America is struggling very hard. That the obesity is now, is taking a toll all over the world because of the junk food that we are eating every now and then. Jeffrey writes, does gamma change the mass of the Z number? No, no, no. Jeffrey, no. The Z number doesn't, G number, what we call Z number, and in India, Z is called Z. But others, in native speaking countries, Z is called Z. The Z number doesn't change because, G number changes by the emission of alpha, beta, and positron. The gamma is a free, just like it everywhere. I've gone to supermarkets everywhere in the world. Buy one, get one free is not common in India. It is a common feature elsewhere in the world. So buy one, get one free, or buy two, get one free. Sometimes buy one, get two free. I don't know. So gamma is a free thing that happens due to the consequence of alpha emission or beta emission. Usually positron emission, of course, positron emission does involve the production of gamma. I'll tell you that sometimes what happens, if a particular radioactive element is a positron emitter, I'm not going to discuss the details, which one is a positron emitter, which one is an alpha emitter. If some radioactive nuclide is an alpha emitter, it is an alpha emitter. There are few radioactive nuclides which go parallel. They go for parallel reaction. Some of them decay by alpha route, and some of them go by beta route. There are few nuclides which go parallelly, alpha and beta, but their number is very small. I'll show you, don't worry. But those who are positron emitter, the lighter nuclides, they are positron emitters. You will not find heavy nuclides like thorium, actinium, protactinium. These are never ever produce positron. But when a positron comes out, sometimes before going to the atmosphere, it captures an electron from the outermost shell. I remind you, positron is coming from the atomy. When it comes out, it captures an electron from the outer cell. And when, perhaps I have not, guys, I have not done any lecture for you this year for the particle science, the particle physics, that when a particle and its anti-particle, they combine, the two particles, one particle, the other one is anti-particle, or as we call antiparticle. When they combine, immediately they die. and they convert into pure electromagnetic photon. So when a positron comes out from the nucleus and it combines with a outermost electron, then the two undergo annihilation. That process is called annihilation. 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 That means they destroy each other, and in turn, we get two gamma photons, sometimes three. So I have made a video describing the details how when two gamma photons are produced and sometimes three gamma photons are produced. So I'm not going to the details. And that gamma photon which is produced, the two gamma photons are usually produced going in opposite directions. They are used now in the recent testing equipment called PET. PET. Do you know what is PET? PET scan, positron emission tomography. PET. So that positron emission tomography is now, they are more advanced than MRI, the magnetic resonance imaging, and its elder brother is PET. If I don't know what charge, Jeffrey, you guys are giving, you guys are all are insured, but here most of us are not insured. So we have to pay for MRI. MRI costs now, I think, 6,000 minimum. INR. You divide by 85 or 87 to get into dollars. And PET scan is 35,000 INR. So definitely it's the elder brother. So that is positron and electron can combine, and before they destroy, they produce an exotic particle called positronium. Positron will be at the center, electron will be rotating around, and that exotic particle which will be produced for a very, very short time, its half-life period is maybe of the order of 10 to the power minus 10. So they will immediately burst into 2 or 3 gamma photons. Now come back. Yes, gamma is a gift, because the nucleus goes to a higher energy level. When it returns back to the ground state, it emits gamma. And sometimes positron, electron annihilation also produce gamma. This is another way but that is rare. Positron emitters are not common. They're uncommon. Lighter nuclides, synthetic nuclides, like carbon 11, like potassium 38, like sodium 22. The mass number is less than what the nature has produced. They are positron emitters. We are not going to the details of that. Now, a healthy, a normal person emits, each of us emits 4,400 beta particles from potassium 40 that we are eating banana and different fruits and vegetables, and 3,000 beta particles from carbon. Carbon 14 is there. Wherever there is carbon, there will be carbon 14. They are natural. So altogether, maybe 7,000 beta particles we are emitting per second. Per second. Can you imagine? So each of us is radioactive. Banana and other eatables, vegetables contain K40. K40 percentage is very low, but that low makes us radioactive. But we neither are being a threat to the environment, nor we are polluting the environment, because that is below the tolerable limit. Greater than acceptable human limits is dangerous. Otherwise, it's nothing. So we should not be scared of radioactive elements unless we get an overdose of the rays more than the acceptable human limits. Jeffrey, am I clear to you? Is this related to electron capture? No. Yeah. I'm showing you. Yes, Jeffrey is very... now, I'm showing you what is the difference between the positron emission and electron capture. This is analogous, but they are slightly different in their mechanisms. Just listen to me. Now, the half-life periods, is the time needed for a radionuclide to reduce to half of its initial amount. Because later, if you are a lower level school student, maybe ninth grade or 10th grade, you might not be knowing about the rate of decay, the kinetics, that there is a different style of the process. This process is called a fast order process. In a fast order process, the decay or the change is independent of the initial amount. Supposing you have 20 gram, and to become half of 20, that means to become 10, you need, supposing, 10 years. And the 10 gram to convert to 5, it's half, another 10 years. To 5 gram to become 2.5 gram, another 10 years. So the half-life period is independent of the initial amount. So it goes for a long time, and we consider, after you will calculate, after maybe 5 to 7 half-lives, almost 99% of that original material is over, and we say it is done. But theoretically, if the graph is hyperbola and it doesn't meet the x-axis, it never finishes. But practically, after 5 to 7 half-lives, it is gone. That is why many of the naturally radioactive elements are not now present, because of their low half-life periods. They were there once upon a time, but they are now almost extinct, almost. They're still there in trace quantity. Sorry, please allow me to have a sip of tea. Now, uranium 238 has a very long half-life. It is almost, comparable with the age of the universe. Therefore, uranium-lead dating is done to find the age of the universe. The half-life period is so high. Radium 228 isotope is only 5.8 years, but another isotope which is more abundant, I mean, they are not really, high, highly available. Radium is having, it is a scarce element, but it is being produced, it is there. We can synthetically also produce radium. 226 has 1599 years half-life. Thorium 234 is only 24 days, but the thorium ores is 232. That is 10 to the power 10 years more than the age of the universe. Protactinium is only 1.17 minutes. Polonium is only 0.15 seconds. And the recent organation 118 has only 0.9 millisecond. Now they have created one atom per experiment. They create only one atom, and that die after 0.9 millisecond. But maybe time will come. The time will come when you will be grown into a full, a big man. Then you will find that they must have prepared organization in bulk amount. That then they will study their properties. Now they are predicting. Now, I would definitely tell you that all the natural radioactive elements, isotopes, they fall into 4 natural series. One is called the uranium series. The other one is called the thorium series. Uranium series is called 4n plus 2, because all the isotopes will fall into the 4n plus 2 rule. If you equate the isotopic mass number is equal to 4n plus 2, then n you will find a whole number. That means subtract that number, isotopic number, minus 2, make that minus 2 and divide by 4, you will get a whole number. So all the isotopes in that particular family, this is the family tree, the top is someone, and the descendants will be all falling under that particular family, 4n plus 2 or uranium. Then thorium is 4n. Then actinium is 4n plus 3. And neptunium is 4n plus 1. And the beginning, the grandfather, I mean, not great grandfather, is uranium 238 for 4n plus 2. And I have already told you the half-life. And thorium, it is not thorium. It is thorium, I'm sorry, thorium 232. I'm so sorry. Thorium 232 is its great grandfather, from which descendants will come up. Actinium is actinium 227. But actually, the original grandfather is uranium 235, which is present in the uranium ore. So the uranium series and actinium series, they're together found in the uranium ores, like pitchblende, monazite, clevite, and all that. So uranium 235 does not belong to the uranium series, 4n plus 2 series. It belongs to the 4n plus 3, because if you subtract 3 from 235, it will be 232, and then divide by 4, it will be 4 5s are 20, then 32, then 4 8s are 32. So it's a whole number. but 238 comes in the formula of 4n plus 2. And another series is a neptunium series. Neptunium is now dead, almost defunct, I mean extinct, but it was there. It was there and it is there, but in less quantity. But all its descendants falling into the formula 4n plus 1, they are there. Now I'm showing you, just see. That will make you in another 15 minutes, we will be winding up this, how the new synthetic elements are being prepared, are being synthesized. There are 3 laboratories which are at daggers drawn. They are friends, but they compete with each other. One is at California, where I stay, in that state, that is in Berkeley, University of California, Berkeley, and they have separated the laboratory. The nuclear laboratory is now separate from the University of Berkeley, University of California, Berkeley. And the other one is in Germany, Darmstadt. Darmstadt is a city in Germany where this nuclear research goes on. And the most challenging one is in Russia. In Russia, it is in Dubna, close to Moscow, Dubna city. So Dubna, Darmstadt, Germany, Dubna, Russia, and Berkeley in US. These 3 places are the centers where we have cyclotron. Cyclotron is a device which makes the projectile, the particle which will hit on you, I mean the target, high speed by the use of the electric field and magnetic field. They accelerate in a spiral path, and when after a long distance of experiencing electric field and magnetic field, it will acquire very high speed, maybe 1/3 of the speed of light, maybe less than that. Then they will be allowed to hit on a static target. Then after that, it will enter into the Tommy. That projectile will be entering into the Tommy, and after it mingles with the Tommy protons and neutrons, then something happens, a new element is created. But in most of the cases, some little particle, maybe 1, 2, 3, 4 neutrons or some other particle goes out on the other side of the Tommy, I mean from that body. So this is a, normally we call nuclear transmutation or nuclear transformation. That happened, when Lawrence was the first person to discover cyclotron, I mean to prepare, to fabricate cyclotron device. Nowadays, cyclotron is only used for low grade research. They have been superseded by synchrotron. And super synchrotron, as some other time I'll be having a lecture on the Large Hadron Collider. Nowadays, this acceleration of particles, they're being made in synchrotron and super synchrotrons. Cyclotron is the beginning, is the first device to, these are called particle accelerators. Particle accelerators are called cyclotrons. So I will tell you that. Please bear with me. I'm sorry. I'm getting dry. Now, the uranium series starts from the great grandfather uranium 238. And then it is an alpha emitter. It is an alpha emitter, not a beta emitter, alpha. That means the new daughter will be having 2 atomic number less. That means it will be found 2 places to the left is thorium, and its mass number is reduced by 4, because it is helium He24. So mass number will be reduced by 4, atomic number will be reduced by 2, and you identify the new nuclide from its atomic number, thorium. Thorium 234 is a beta emitter. So the new will be having 1 place to the right, protactinium. And the half-life periods are written. Thorium 234 is only 24.1 days. After that, it will be halved. And this protactinium is 1.16 minute. And after it gives a beta particle, it becomes uranium 234. 234 is a part of this uranium series. Then it is an alpha emitter. So during the process, buy one, get one free, gamma is emitted every time. So if any radioactive materials, gamma is free. Buy one, get one free. So alpha is coming, beta is coming in that particular mineral. Alpha is coming, beta is also coming. That doesn't mean that uranium 238 is a beta emitter. It is an alpha emitter. This is a beta, alpha, 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 beta. Here, you don't have a parallel reaction here, but in other series you find parallel reaction. A certain radioactive nuclide will be having alpha as well as beta, but in different rates. And then that one will be merging into, that if this is alpha, then the other one will be beta. If this is beta, this will be alpha. So that it will be merging to the same. I will show you. So ultimately, unless a stable non-radioactive nuclide is not formed, it continues its series. So after so many nuclides, you are getting lead. So lead is created, lead 20, not only lead 206, you have to say that, is produced from the uranium series. Now I'm showing you that after ejecting an alpha particle, uranium becomes thorium, this one. And thorium being a beta emitter, it gives protactinium, because you have to add these lower numbers, which will tally with the lower number of the mother, and you add the upper superscripts, you will also tally with the superscript of the mother. Now this is thorium series. You will find the beginning grandfather is thorium 232, and in the world, US is the leading producer of thorium ores, and India is also not lagging much behind. We have a lot of thorium deposits, thorium ores, that is thorium 232. But you will know later, this is not the time to discuss about the nuclear fission to bring about energy. But thorium 232 is not a fissile nuclide, but it can be easily converted to uranium 233 in a breeder reactor. In a breeder reactor, thorium 232, which is abundantly present because of its so large half-life period, 14 giga years, or 1.4 into 10 to the power 10 years. So we can easily convert to uranium-233, which is fissile, and we can fission by applying thermal neutrons or slow neutrons and bring about a lot of energy that we are doing with uranium-235 and plutonium-241. We are doing that. So the bomb that was dropped in Hiroshima by, US in World War II was a uranium bomb, uranium-235. And the next day, Nagasaki was also being bombarded by another bomb, the plutonium bomb, plutonium-241. So fissile nuclides will have odd mass numbers, but the vice versa is not always true. Not all odd mass number radionuclides are fissile. So we are not going to do that. So in this series, you find here polonium-216. This left word is alpha, the right word is beta. Some of them goes by alpha decay, some of them goes by beta decay. So it gives two different isotopes, polonium, lead 212 and astatine 216. But this is a beta and this is an alpha. So ultimately, it gives bismuth 212. And ultimately, the stable nuclide is again lead 208. And I've shown you how this thorium is an alpha emitter and its daughter is radium-228, and the radium is a beta emitter, its daughter is actinium. This is here, actinium-228. So the actinium series, actually, it starts, we call it actinium series here, but actually, since uranium series, the name uranium is already there, so we don't use the term again uranium series. We give actinium series 227. It falls into 4n+3 rule, but its real starter is uranium-235, which is available in the uranium ore only by 0.7%. That is fissile. That is why India and many other countries like us, we will never call us as a poor country. We are not rich as the West, but we are developing country. But they call us third world countries anyway. We bear that. And uranium-235, 0.7%. Sometimes we need more. The enrichment of uranium ore is necessary when we use light water, ordinary water, as the coolant, as the moderator. But heavy water, we have to have a lot of heavy water. India has more than 7 plants which produce heavy water, D2O, which acts as a moderator and a coolant for natural uranium ore. But if you want to use enriched uranium ore, 0.7% uranium-235 has to be enriched to 2%, 3%, that we are not able to do. It's very, very cumbersome process, and we not beg. We buy from France, US. We had a ban for long years. They were not supplying to us, and our light water plants were not working. And after some time, they started giving us the enriched uranium ore, which contains 2 to 3% of uranium-235, which is the real hero. They undergo fission and they give us energy, not uranium-238. Okay, we're not going to talk about the details of fission. Now you see uranium-235 having such a large half-life period, and then it gives thorium-231. You have seen thorium-234 in the uranium series. 232 was the great grandfather of the thorium series, and now 231 falling in the 4n+3 series, then protactinium, then actinium, as we call it, actinium series 227. And ultimately, and there is also a parallel reaction here, bismuth 211. It goes for a parallel reaction, beta and alpha, and ultimately land at the stable 207 lead isotope. Now see. This is the last series, the Neptunium series, which a beginner is americium-241. So they believe, sorry, plutonium-241. So they believe that the plutonium is there. It is natural, but scarce. We synthesize. But they believe that americium, now this is the first time I'm saying that americium also might be there in the nature, but it is not being found in nature. It is prepared because its half-life period is 4.7 years only. And the, till now, the universe has elapsed 13.7 billion years. So it is not there. Then Neptunium. Neptunium, we are giving the name of the series as Neptunium-237. And then it is a alpha emitter, gives protactinium. Protactinium is a beta emitter, gives uranium-233. This uranium-233, whose half-life is so high, so it is there in the series of Neptunium. But Neptunium is present in a small quantity. So from the mother, which is present in small quantity, the uranium is also present in uranium-233, which is a superhero. The future hero is uranium-233, which is fissile. Is not much in this series, but we have to convert thorium-232 in a breeder reactor to uranium-233, which is fissile, and the future energy program will be thorium. In fact, thorium car is coming by a American company who has challenged, and by 2050 they will be producing thorium car, which will be totally outsmarting the EVs. Once you buy that thorium car, it will not need any fuel for the lifetime. The lifetime of a human being, say max 100 years. But that will remain, because the half-life period is so high that it will remain until and unless it crashes. It will remain for years to come, more than the lifespan of a human being. So that is the, you guys who are young, you will be, taking the benefit of the thorium car. Now, this is also having a parallel reaction here, bismuth-213, and ending in bismuth-209. Okay, then positron emission, as Jeffrey is still, are you still watching, Jeffrey? Does plutonium have similar alpha decay as uranium? He is there. Plutonium has similar alpha decay as uranium. Yes, you see, plutonium, plutonium 241, unfortunately, it is a beta emitter. 241 is a beta emitter. I'm not talking, no. Plutonium 241 is a beta emitter. It is giving americium, and then americium is an alpha emitter. It is no. Well, let me tell you, Jeffrey, that when in a breeder reactor, we take uranium-238, which is abundant, 99.3%, and we hit, neutron onto it. It captures the electron and becomes uranium-239, which is unstable, which is a beta emitter, gives Neptunium-239. And Neptunium-239 is also a beta emitter. That gives plutonium-239. So, plutonium-239, let me ask to the Google. Plutonium-239 is a beta emitter? Question mark. Today, Google, Dr. Google. No. Jeffrey, even plutonium-239, which is fissile, but having a small half-life period, we are more banking on plutonium-241, which is synthetic. Plutonium-239 also is a beta emitter. So I think I have answered your question. The answer is no. The answer is no. This plutonium-241 is beta. plutonium-239, which is produced in the breeder reactor, is also beta. Okay. Now, positron emission is the decay mode for lighter nuclides having lower mass number than what the nature has provided, as we sometimes call God has provided. So carbon-11 is not a natural isotope. We have prepared it, the synthetic isotope. Once we prepare carbon-11, then you will find it is radioactive, and that is a positron emitter. So once positron is emitted, undoubtedly, the new daughter will be having a one place to the left. The new daughter will be not carbon, it is boron. Oh, you forget about this. This is a neutrino, which is produced buy one, get one free when a positron is emitted. This is electron neutrino is produced. And when a beta particle is emitted, anti-electron neutrino is produced. So you forget about these neutrino particles, which are again buy one, get one free, like gamma. Gamma is, of course, a photon, but neutrinos are particles having negligible mass. So forget about this. So carbon-11 is a positron emitter. So it emits a positron, and the new daughter becomes one place to the left, boron. But similarly, magnesium-27, carbon-14, which is a natural isotope, is a beta emitter. We know the half-life period is so high, but this positron emission half-life period is so low, 20 minutes. Similarly, magnesium-23, because the God-made magnesium is 24. So 23 is man-made, synthetic, and that is a positron emitter, and the new element, new nuclide produced is sodium-23, which is normal. Similarly, magnesium-27 is a beta emitter, and the daughter nuclide is normal aluminum-27. Okay. So whenever positron is emitted, an electron neutrino is produced. Whenever beta particle is produced, and anti-electron neutrino is produced, buy one, get one free. Forget about, gamma. Gamma is buy one, get two free. So K-capture is analogous. Jeffrey, you are watching. It is analogous to positron emission. But what happens? Such nuclides having lower mass number than expected from nature, that sometimes decays by K-capture. One electron from the K cell, K, not the outermost cell, the first cell, which is nearest to the nucleus. So the nucleus captures, that is why it is called K-capture, captures one electron from the K cell, and what happens? 53 minus 1. The electron now combines with a proton and becomes neutron. So one proton is reduced, so the new element again occupies one place to the left. Just like positron emission, and like positron emission, buy one, get one free, electron neutrino is produced, so electron neutrino is produced. That is by default. So that is a conservation of lepton number. So we are not going to talk about the lepton number conservation or the quark number conservation. We are not doing baryon conservation. We are not doing about that. And aluminum-26, not 27. 27 is stable. 26 is a synthetic isotope. Sometimes it will be decaying by positron emission. Sometimes when its mood will be saying no, I will not eject out anything other than the neutrino. Okay, it will capture one electron from the first cell, and it will give the same daughter. I mean, one place to the, not same. I mean, one place to the. I said same to compare with the positron emission. So the new nuclide will be magnesium, and that is also not stable. Magnesium 24 is stable. So then it will go again in a series. That this is called a synthetic radioactive series. Until and unless a stable nuclide is produced, even there will be a series from the synthetic radioactive nuclides. So K-capture is analogous to now the last is the nuclear transmutation. So I told you cyclotron is the device in which we take the particle X. X is particle P. P is the projectile particle which we will be giving high speed inside the cyclotron, moving in a spiral path and gaining high velocity in high acceleration, and it will be allowed to hit on a static target. Now this P is projectile, and X is the ejected particle. I told you some particle will go behind the atomic, other side. The ejected particle, T is the target, and R is the product, is the residual nucleus or the product nuclide. So this is called the TPXR type of reaction. Now I have already discussed everything. This is the Berkeley, University of Berkeley. For the first time, Ernest Lawrence in 1930, he devised the first cyclotron device to accelerate the electron in a spiral path to hit on a target. This is the target where the electron comes, not the electron, the projectile. Maybe it is a alpha particle, maybe it is a beta particle, maybe it is a deuteron, it may be a triton, or it may be a calcium 48, or oxygen, maybe neon, whatever you want to use as a projectile. Start from the center. It will be spiraling in a spiral path in a cylindrical tube. Now this is cylindrical, and finally it will be gaining high speed, and that will be allowed to hit on the target. Right? Now this is Lawrence, who got the Nobel Prize. This is another, now in the recent, in the same University of Berkeley, now Berkeley Nuclear Research Center. Now see, if I write beryllium 49 alpha N reaction, the first will be the projectile. The first one inside the square bracket is the projectile, and the second one is the ejected particle here. And this beryllium 9 isotope is the target, and this is the residual, the product nuclide. And this experiment was done by Chadwick in 1930 to discover neutron. Beryllium was the target, and alpha, this is helium-24 means alpha particle. So that will be subjected to high acceleration in a cyclotron, and it will be hit on the target beryllium 9, and it was found, to the utter dismay of Chadwick, that on the behind the target has transformed into a new element, carbon 12, which is stable, and neutron is coming out behind it. So he experimented that particles coming out continuously. These are neutral particles. So they already knew that nucleus was containing some neutral particles. Undoubtedly, the proton number is not matching with the atomic mass. Therefore, some neutral particles are definitely there. But there was no proof until Chadwick discovered that neutral particles are nothing but neutrons. Now, if I say write the arsenic 3375 alpha N reaction, you take this as the target, right in the left, and alpha as the projectile, and then write the ejected particle, neutron 01, then calculate 33 plus 2, 35. So this is no charge, so the charge will be 35. And 75 plus 4, 79, minus 1, 78. So the new daughter, here we don't say daughter. This is the residual or the product nuclide is bromine 78. That is also radioactive. This is synthetically radioactive, which will be, I think you can tell me. Can you guess bromine 78 will be a beta emitter or a positron emitter? Lighter nuclides cannot emit alpha. Alpha is a massive particle, 2 protons and 2 neutrons. You know that is the prerogative of heavier nuclides, not the lighter nuclides. When I say lighter, I mean below 83. Below 83, I am saying which are radioactive, which are not radioactive, which are stable. But we can synthesize. Now we have synthesized by an alpha N reaction to arsenic 75, bromine 78. Can anyone answer bromine 78 is what kind of emitter? Oh, last chunk, last chunk, hello? And you are from which place? Last chunk? Hello, last chunk, you are from which place? If you are watching last, your name is very, very funny and very, very interesting. Good. I don't think your name is last chunk, but you might have made your identity as last chunk. Where are you from? Mr. or Miss, I don't try to, locate. Jeffrey says beta minus. Now, anyone who is watching, Steve, what do you say? Bromine 78 will be decaying as what? Will it? It cannot emit alpha, either beta minus or beta plus. Jeffrey says from Miami, US, Florida. Am I correct? It's Miami comes under Florida state? Yes, Jeffrey? Is my knowledge in geography is a little poor, but since I'm acquainted with US, I think it is in Florida. The last part. No, you Siv, are you listening to me? Are you there?
Yes, sir.
I told you that God or nature has made 2 isotopes of bromine. Bromine 79, bromine 81. Both are stable and with the relative abundance 50-50. 1:1. Yeah. The Florida, Miami is in Florida, and you are from Florida International University, that is in Miami. Florida is a big state, but not as big perhaps as California. Tallahassee is in Tallahassee. Florida State University is in Tallahassee. Yeah. I can't pronounce the term Tallahassee. Okay, we will meet sometime. Now, bromine 78, Jeffrey is a positron emitter. 79 and 81, they are natural and stable. Anything below 79 will be positron emitter. Anything above 81 is a beta emitter. I am not going to discuss about this band, the stability zone, and if some nuclide falls below the stability zone, it will be a positron emitter, and some nuclide is falling above the stability zone is a beta emitter, so that it will try to bring back the neutron-proton ratio to the stable one, falling in that stability band. Not going to, yes, this will be, if you are asked to write down what is the product, this is 735, 78, it is a positron emission. I have already, I've told you that it is a positron emitter with +1 and 0 is the mass, almost 0 +1. So the new daughter will be one place to the left. Can you tell me what is 34? The identity will be different. What will be the element? Just look to your periodic table that we have made with this song. Now, Jeffrey, we have, produced a song, periodic table song, with the inspiration of the periodic table song that your XII science in US has produced. And I will be giving you the link maybe now. and just to have to watch it and tell me, I'm giving you the link of that periodic table song that we will be following in India. And this is in English, you can understand. But our pronunciation will be definitely different from yours. So I have done it a little slow pace so that we are non-native speaking countries. So we and other so many non-native speaking English countries will be benefiting from this song sooner or later. So what is the new element, Siv?
Sir, selenium.
Precisely selenium. 34 is selenium, is the new nuclide. We don't call it daughter. Daughter word is used when it is a spontaneous decay. No, this is a projectile hit upon a target. This is a projectile. This is a target. This is a residual or the product nuclide, and this is the ejected particle. As we have written, what symbol we have given in that, particularly in that. This is what we have given X. The ejected particle we have given X. Now see. Now, this is a positron emitter. I'm sorry, Jeffrey. Now, see, in the similar manner, if you hit a deuteron, which is an ion produced from deuteron, you hit on aluminium and they found the ejected particle was found to be alpha and the residual particle was magnesium 25. Magnesium 25 is stable. I have given you the list of all stable nuclides you'll find. And aluminium NP, neutron is the projectile and proton is coming out as ejected particle, and magnesium 27 is being produced, and that is a beta emitter. I told you that magnesium 24, 25, they are stable. 24 is the most abundant isotope. So we are taking the average of 24 for magnesium, but 27 is radioactive. Magnesium 27 is radioactive. Yes. Yes. It is synthetic. And you can say, can you tell me which emitter will be magnesium 27? I told you the general principle. Yes. Jeffrey, if you are still there, and we'll be winding up in another 10 minutes, please bear with me, because I'll tell you in the climax how these guys, the three laboratories which are competing with each other, one at Berkeley, the other one is Dubna, Russia, and the third one is in Germany. These are the three places where some work is going on in Riken, Japan. So these four places are always working, and so yes, Shiv, magnesium 27 is what kind of emitter?
Sir, beta emitter.
Precisely beta emitter, because more than the normal, you will be making its N by P ratio falling more than the stability band, and it will stabilize itself by emitting a beta particle. You can write down the product similar reaction. Now, technetium, how technetium was prepared? Technetium is 43. Now it is almost extinct in nature. We are preparing technetium for our SPECT. Imaging. It can image all the organs inside the body and tell whether you are having a tumor, cancer, whatever. Technetium is now the most important nuclide, radionuclide, and 99 isotope is being produced. Now see, this is uranium 238 spontaneous fission. The percentage is less than 0.05%. Uranium 238 is not fissile. Uranium 235 is fissile, which is only 0.7%. We enrich it to 2%, 3%. And the guys who prepare atom bomb, they enrich it to, maybe 35, 40, 50, 100%. Spend a lot of money and all that. If it is 100% or maybe 80% of uranium 235, then it will be a bomb, an atom bomb, right? So, but maybe 0.05% of 235 undergoes self fission. This is called spontaneous fission to give you iodine and yttrium with 2 neutrons. And this yttrium-99 is a beta emitter. It gives zirconium one place to the right. Zirconium is a beta emitter. See their half-lives so small, 1.47, 2.1 second. This gives niobium 99 isotope, which is a beta emitter. Gives molybdenum, which is a beta emitter. This is a series, a synthetic series. This is 65.94 hours. And finally, we get technetium 99, which has got a very high half-life of, 1, 2, 3, 1, 2, 3, 4, 5, 2.11 into 10 to the power 5 years. So once we prepare, isolate technetium 99 from this, but this is very, very small. Nowadays, we are preparing in another way by a molybdenum, deuteron, neutron transmutation. We are taking deuteron as the projectile in cyclotron and hitting on molybdenum 99. This molybdenum 99 you also get from other sources, and we are getting technetium 99 and 2 neutron and as ejected particles. So there are many ways how to get technetium. So also we are getting promethium 147, which is extinct by the normal fission. This is called induced fission. The normal fission that we say fission, it is induced by slow neutrons called thermal neutrons, and it gives 236, but it is unstable. It gives several pairs of, they're not called daughter nuclides, the lighter nuclides. One of them is promethium 147. You can also get a neutron beta reaction, transmutation reaction. Heat neodymium 146 with neutron, because neodymium as we pronounce, neodymium is one place to the left, which is available as a rare earth. Name is rare earth, which is a misnomer, is available. Hit neutron continuously, and it will give ultimately after beta emission, it will give you promethium. So there are ways. Now see how astatine and polonium are synthesized. Same projectile in cyclotron, target, and you get ejected particle, firing alpha particle with bismuth, normal bismuth 209, they get astatine 211. And this is very much required in our radioactive research, in medical research, astatine. Its lifetime is 7.21. Lifetime means half-life. Then there are so many other methods. Alpha particle, sometimes 3 neutron gives 210 isotope, 2 neutrons 211, 4 neutrons 209. Then how polonium is synthesized by heating same bismuth with a deuteron, even proton. So you get 209 and 208 isotopes. Now 209 hit on neutron, it gives a gamma photon, no other particle. Gamma, buy one get one free. So I have written in a very condensed manner in above the arrow mark, n gamma means hitting the projectile is neutron, and the ejected particle, yes, it is a particle, photon is gamma. Then bismuth 10 is unstable, it is a beta emitter and gives polonium. So there are many ways how. This similar manner, francium is produced. This looks very small. You can heating oxygen 18. Oxygen 18 is a stable isotope present only in 0.02%. 0.02% they have to isolate. How much cumbersome and expensive the process. O18 is the target. And gold, normal gold 197, O18 is the projectile, and normal gold 197 is the target, and you are getting francium along with 6 neutrons going away, francium 209. So oxygen, there is parallel reaction where 4 neutrons goes, then you get francium 211 isotope. So both 209 and 211 isotopes are produced. Similarly, radium can also be produced, and now we are heading towards the transuranic elements. Neptunium is produced. I told you in the breeder reactor, uranium 238 becomes 239, which is a beta emitter, gives neptunium. Then neptunium is a beta emitter, gives plutonium. Plutonium, when fired by alpha particle, it gives curium 96. And neutron. When plutonium is hit by neutrons, it gives americium. When americium is hit by alpha, it gives berkelium. When curium is hit by carbon 12, carbon 12 is the projectile, it gives nobelium. See how, these three places, supposing one laboratory is initiating, immediately other two laboratories are confirming. Now see how heavy transuranic elements are produced. Heavy transuranic. The plutonium is hit by neutron. It gives 4 neutron. It gives in 4 steps, 4 gamma. In each step, 1 gamma. So finally, 4 neutrons are added. 9 plus 4, 43. So you're getting same plutonium 243, which is a beta emitter, giving 1 plus to the right americium. Then again neutron heating doesn't give any, buy one get one free gamma goes, so it becomes same americium 244, which is a beta emitter, gives curium. Curium is hit upon 5 neutrons successively to give you curium 249, which is a beta emitter, gives berkelium, which is another berkelium. I told you that berkelium and californium, up to californium, scientists have synthesized in some bulk quantity to make them target. Unless we prepare some material in some bulk quantity, they cannot be used as a target. If you prepare some few atoms, like 10 atoms, 100 atoms, they cannot be used as a target. Now, finally, berkelium is a beta emitter, which gives californium. Californium, then neutron bombardment gives you californium 253, which is a beta emitter, gives Einsteinium. Einsteinium neutron bombardment gives Einsteinium 254, which is a beta emitter, gives fermium. Then another one is uranium 238, hit upon by oxygen 16 will give you fermium 250. This is fermium 254. This is fermium 250. I'm showing you how the transactinide or the super heavy elements are produced up. So similarly, mendelevium is produced by the alpha firing onto Einsteinium. Carbon firing onto curium gives nobelium. Neon 22 firing on uranium, giving again nobelium. Boron 11 firing on californium gives lawrencium, the last actinide element. And also oxygen 18 firing onto americium gives lawrencium. Now coming to the post-lanthanide elements, super heavy elements, californium, I told you, you will not take any element as target which has not been produced in bulk quantities. Californium heat fired by carbon 12 gives you rutherfordium. Then americium hit by neon 22, dubnium. Californium hit by oxygen 18 gives seaborgium. Bismuth by chromium. Chromium is 54 mass number. It will be the projectile in the cyclotron. Bismuth is the target, gives you borium. And bismuth hit by manganese 55 will give you hassium. Bismuth hit by iron 58 is these are not the stable isotopes. Iron 56 is stable. So 58 is hit upon by bismuth. It gives meitnerium 266. Nickel hit onto lead 208 gives dermstatium. Nickel 64, here it is 62, 64. Hit upon bismuth gives röntgenium 272. And finally, zinc. Can you believe zinc is made as a projectile? Zinc 70. Zinc 70. It means a projectile to hit on lead 208 to give copernicium. In the similar manner, bismuth zinc will give you nihonium, plutonium, calcium. Calcium 48 is a natural isotope. And it is almost stable. It is actually, the half-life period is 10 to the power 15 years. So it is taken to be stable. So this is a natural isotope. They have to isolate from the calcium all other isotopes. There are 5 stable and 2, So you have to isolate calcium 48 and then heat on plutonium to give flerovium, calcium 48 with americium, moscovium, calcium 48 with curium gives livermorium. We have not exceeded californium. No element has been used as a target beyond californium. Beyond californium comes Einsteinium. You never find Einsteinium. Einsteinium has been used but maybe later when Einsteinium will be prepared in bulk quantity, they can use Einsteinium as a target and make another new element. Who knows what will happen in future? So organation is the last one. Calcium is heat up on californium. Now they are planning for 119. They're planning, oh, I have given you the lifetime, they're very small, ranging from few minutes. That is why they are not able to prepare in bulk. Organization 0.9 second, livermorium 80 millisecond, is 0.9 millisecond, dumb stadium. As you go nearer to californium, you will find the half-life period will be slightly increasing and increasing and increasing. And you see Einsteinium, which is coming after californium, is 39.80 days. Who knows? In very short time, Einsteinium will be prepared in bulk quantities because its half-life period is not that very low. So immediately they will make it a target and hit on some projectile to get new element. So this is the end of our story today. Thank you very much for giving your valuable time to be with me. And the last line that Jeffrey writes, you have a pleasant voice. I like the catchy periodic table song. And Jeffrey, you could share your email ID with me. I am sharing my email ID. We'll be in touch. So this is Sudhansu Tripathy from, originally I am from here, India, and Odisha is the state, and Cuttack is the city where I was born, and maybe I will die here. Who knows? Maybe I used to go to US every year. So who knows? I will die in California and in San Diego, and I'll be cremated there. And I opt for electric crematorium there. Periodic table song. Thank you. This is sudhansu.trips@gmail.com. You can just copy if you want. Sudhansu, SUDHANSU .trips, TRIPS, then @gmail.com. We can have, yes, I have written that. So guys, this is the end of the 3 days program that we have been celebrating the periodic table day starting from 7th of February, in which the John Newland's first time proposed the periodic table with the law of octaves, do, re, mi, fa, sol, la, ti, as the Western notes call C, D, E, F, G, A, B, again C. Law of octaves. And yesterday, 8th of February, was the birthday of Dmitry Mendeleev, who is the father of the periodic table. And today is the spillover. Buy two, get one free. So today is the culmination, the end of the periodic table day celebration. Guys who have watched this, and who will be watching, many guys will be watching later, and those who are joining in Zoom, like Anisha, Siddharth, thank you so much for giving me this encouragement to continue with disseminating my experience at this fag end of my career. I am a retired professor of chemistry in one university in this city, that is called Ravenshaw University. So after my retirement, my passion has been not to while away my time, but to study more and more, because every passing day is a learning day. A teacher or a professor is more a student than a student yourself. We are supposed to study more than. So fortunately, I'm doing that to some extent. I'm trying to disseminate my experience. I'm signing out, and any doubt, anything, you can directly contact with me. I've given you my email ID. Bye-bye. Take care. God bless. Thank you.
Pranam, sir.